last few times we've been building up to this point. This is really the heart and core of this section of the class for thermodynamics. It's dealing with the second law of thermodynamics, which is really where everything in thermodynamics comes from. It's the thing that makes thermodynamics unique among all of the other branches of physics and physical chemistry. It's the thing that determines what the true driving forces are that cause thermodynamic changes. And since thermodynamics controls a great deal, an enormous amount of what happens in the real world at the macroscopic scale, it's an enormously important law. I have an extended version of the law, as you can see, the extended second law. This is like the extended first law. It's mostly my own version of the second law with a whole bunch of statements mixed together to give a more complete picture. Some statements of both the first and second law are rather terse, and they don't say enough to really be at all clear. I hope these more extensive and more explanatory versions are more clear. So let's go through this extended second law. First of all, it says four different things here. The first one is for an isolated system, notice, we'll talk about non-isolated systems later, but isolated systems are easier, so we start with that. For an isolated system, the equilibrium state is the macro state. Remember, a macro state is a collection of microstates, a large number of microstates usually. It's the state that maximizes the entropy. We've already seen what the entropy is. It's the number of microstates in a macro state. And now we're saying that if the entropy is maximized, if you change things, allow things to change until the entropy is maximized, then that state, that at the end of that process, will be the equilibrium state. This is the important statement, really. It establishes a maximization principle in thermodynamics, and from a maximization principle, you can derive all of the other properties and driving forces and changes that make thermodynamics work. Second statement, the entropy S is a state function. We've seen what state functions are. Everything's a state function except for heat and work. Of these variables, these are the natural variables. You can change those variables if you like, but these particular variables are especially useful and especially appropriate for the entropy. And I don't know that we'll go deeply enough into the theory in this class to really explain why this particular set is more important or better than other sets of possible variables. We could, put T and P and various chemical potentials in here, for example. Those would be other ways of expressing the state of a thermodynamic system. But these are the most important ones for the function entropy in particular. And there are other natural variables for other functions like Gibbs free energy and so on, and we'll encounter those as we go along. So it's a state function. S as a function of energy, volume, and the various mole numbers. That's an important function called a fundamental thermodynamic potential. It's one of several different functions, but the most important one, really. The others are all derived from this one, really. That control in all the aspects of how a thermodynamic system behaves. So statements like this are really important because once you know these things, you know that you really just have one target. If you want to understand everything about a thermodynamic system, what you want is this function, the entropy as a function of its natural variables. We won't go deeply into these properties either in this class, because this is an introduction to thermodynamics and physical chemistry. After all, it's not a full class on thermodynamics. But suffice it to say that these kinds of things, the fundamental thermodynamic potentials, are the best way and the most natural way and the most powerful way to express a complete understanding of the thermodynamics of any physical system. Then it says that the entropy is a monotonic increasing function of energy. That means that as the energy goes up, if you were to plot the entropy versus the entropy always increases. It may kind of slow down as energy continues, and it usually does, in fact. But it never dips down and never even goes flat. It always increases as energy increases, and that has some profound implications. We'll see that when we talk about it down below. And finally, number 4, entropy adds over subsystems. That means if I have a system that's got a bunch of subsystems inside of it, and I know the entropy for each piece, then I can get the entropy for the overall thing by adding up the entropies for each of the pieces. That's a powerful rule. It allows us to go from simple systems to systems that are as complicated as we like, just by adding up pieces. All right, those are the 4 parts of this extended second law. Let's go through them one by one now. First of all, entropy is maximized at equilibrium. The system will move towards states of higher entropy. That's what that means, right? If we're heading towards equilibrium, if every system starts out at some point that's not equilibrium, let's suppose we have an isolated, now this is always for an isolated system, right? So let me make sure that's clear. There are equivalent, actually, minimization conditions for open systems, and we'll encounter those. Those are the free energies, Gibbs free energy, Helmholtz free energy, and so on. But for isolated system, it's entropy, and entropy is the most basic and most fundamental of them all. The other ones are really just kind of forms of entropy that have been kind of wangled around into a convenient form for historical purposes. Anyway, what this is saying is that for an isolated system like this, if I start, for example, to pick a concrete, more or less concrete case, with a bunch of particles on one side, a bunch of particles on the other side, and now I start moving this barrier. So I'm not allowing particles to change. I'm not the barrier can exchange heat, let's say, just for concreteness, but I'm moving the barrier so there's pressure on this side, there's pressure on that side. If I watch what happens to the entropy as I move the barrier, so there's an entropy for this overall system, for this total combined system. If I watch how the entropy changes when I move this barrier, what I'll find is that either goes up or goes down. If I move the barrier one way, it goes down. If I move the barrier the other way, it goes down. And the system wants to move towards the place, towards increases in entropy. It wants to move towards the maximum event, ultimately. So if I allow the barrier to move on its own, it will move for a while, and then ultimately it will stop someplace. And the place it will stop is the place at which the entropy is a maximum. And if I started the barrier over here, say, and started moving it this way, or letting it go to go where it wants to go, then it will also move toward this maximum in the entropy. That's what this statement is saying. You can see that what that means is that changes in entropy really are a driving force. The system moves in the direction, and forces will be generated by the system to move itself in a particular direction so as to maximize entropy. And that means also that if you set the small changes, the differential change in entropy equal to 0, that's a condition for equilibrium. You can set up equations that allow you to solve for wherever the equilibrium state is. If this position of the barrier right here happens to correspond with the maximum entropy, then that's the equilibrium position. That's the position where all the forces, thermodynamic forces, will balance. We'll talk about that too, yes. All right. We've seen what this really is about. For a very long time, historically, people knew that all these things were true about entropy, but they didn't know why. We've seen now why. It's statistics that's underlying all these things. As the system moves towards maximum entropy, it's increasing the number of microstates available to the system. It's changing the statistics available to the system. This point at equilibrium is the maximum number of microstates, and therefore the most probable arrangement of matter in the system. And that's why the system moves that way. It's just a statistical effect. It's a result of a combination of statistics and random motion not at the microscopic scale. So it's not mysterious, though it was for a long time. It's not mysterious anymore. It is fairly subtle. There'll be a lot of calculations that we do that don't even acknowledge or recognize that there's any statistics going on underneath. But if you were to set up thermodynamics entirely as a statistical theory, and people do that, people have done that, you could do it, you would get the same results that you get from the traditional way of presenting thermodynamics. We're going to present thermo here in a fairly traditional way, which was developed long before the statistical interpretation was known. So there is no reference to statistics in that traditional presentation. And the reason we're going to do it the traditional way is because there's lots of advantages to that. It's a very practical, most of the easiest and quickest ways to do a calculation are done that way. And so we will do it that way, but you could do it statistically. That's underlying everything. This principle also means that whenever you see something changing spontaneously on its own, without anything pushing it from outside, you, for example, let this suppose this barrier here is pinned to start with. So there's some kind of pin that's holding it in place. You take the pin out, and the barrier starts moving. You know that when it's moving and changing like that, it's a spontaneous change, and therefore there must be an entropy increase that's taking place at the same time. It's an entropy increase that's driving that change. Likewise, if you somehow can measure the entropy and you find out that that entropy change is positive, then you know that that change will also be spontaneous. It works both ways. A spontaneous change and a positive entropy are the same thing. A positive entropy happens if and only if it's a spontaneous change, and vice versa. On the other hand, if you do some calculation, usually is how this happens, and you calculate that the entropy change for some process is negative, then that doesn't mean the process doesn't happen. It means it goes backwards. It means that if you let things go, it will move in the opposite direction from the way you calculated. Another implication is that if I start from one place here, so here's my barrier again, and I let it go, and it starts moving towards, this is the equilibrium state, say. And on the other hand, I start from over on the other side here, and again, I let the barrier go, and it starts moving towards the equilibrium state. Because there's only one maximum in the true equilibrium state, I always will arrive at the same point, no matter where I started out. If I could start the barrier at any number of places, any place that's not actually already at the equilibrium point, and if you wait a while, how long you have to wait depends on the system. Some systems very quick, some systems very slow. The time it varies over enormous range. Some things take geological ages to reach equilibrium. Some things take nanoseconds to reach equilibrium. But eventually, it will arrive at the equilibrium state, and there's only one equilibrium state. It will always arrive at the same state, no matter where you started. Number 2, entropy is a state function. We've already seen what that means. It means that if I have some process, let's say starting with some thermodynamic equilibrium state, state 1 here, and going to some thermodynamic state 2 here, and I do it, let's say, by a nice, smooth, reversible process where we're at equilibrium more or less at every point along the path, and I calculate an entropy change associated with that overall change from state 1 to state 2. If I now imagine another process with a completely different path, an ugly one that doesn't even involve equilibrium states. So let's suppose I have this path, but some of these states aren't even on this chart because they're not even equilibrium states. Doesn't matter. As long as you started at state 1 and you arrive at state 2, the entropy change will be the same in both cases, no matter what happens in between. Same initial state, same final state means same change in entropy. Here's the third thing we talked about. I said it before, that entropy is monotonic increasing, which means entropy always goes up when the energy goes up. Here's that same little chart or plot that I plotted before. And that has several implications. The most important ones for our purpose is that it means that if you have a system and it's in contact with the surroundings, and some heat flows, let's say, from the system to the surroundings. That means the system loses energy, right? That means the energy of the system is going down. That means the entropy of the system has to go down too. You may not know, I mean, until you do a calculation, you don't know how much it goes down by, but you know it's going to go down. If the entropy of the system, if the system lost energy, entropy went down too. On the other hand, the entropy of the surroundings, there is entropy of the surroundings, right? There's entropy of the universe. Total entropy of the universe is the entropy of the system plus the entropy of the surroundings. Surroundings gained energy. And therefore, the entropy of the surroundings went up. And so the question is, what about the total entropy change for the system and the surroundings? Did that go up or down? Well, you can't tell until you do a calculation. This guy went down, this guy went up. Which one was bigger? If this guy is bigger, then the total entropy change went up. If this guy is bigger, then the total entropy change went down. If this guy is bigger and the total entropy change went up, then the overall process would be spontaneous, would go on its own, even though the system entropy went down. On the other hand, if this guy is bigger, then the process won't go, or actually the reverse process will go, even though this guy went up. And it works the other way around. If the energy flow were from the surroundings into the system, then the system entropy would go up and the surroundings entropy would go down. Calculations like this, where we're looking at both the system and surroundings entropy changes, are sort of the heart and core of many of the calculations we're going to do in this class. For example, many people are familiar with this, right? Delta G equals delta H minus T delta S. If I divide both sides by T, delta G divided by T equals delta H divided by T minus delta S. It turns out that this quantity is representative of, it's proportional to, the total entropy change for the universe, both system and surroundings. This term represents the delta S change for the surroundings, and this term represents the delta S change for the system. So all these calculations we're going to do later that involve delta G, Gibbs free energy changes, are really disguised calculations for calculating the, in a simple way and in a straightforward and easy to do way, methods for calculating both entropy change in the system and surroundings at the same time. All right, the other implication of this rule is that if I take the slope of this curve, it will always be positive, right? If things are always increasing, and no matter where I am, no matter where on this curve I take the slope, it's always going to be tilting upwards. It's always going to be a positive slope. And it turns out you can show, we will show later, not too long from now, that the derivative, that slope, the derivative of the entropy with respect to energy, is 1 over the temperature. And that always has to be positive, which means that the temperature always has to be positive. So the rule that probably all of you have heard, that you can't have a negative temperature, it comes from this property. It comes from the fact that when you increase the energy of something, you're also increasing the entropy of something. Let me say something else about what this means microscopically, right? When you increase the energy of something, you're increasing the ability of the system to move and change, and therefore it seems intuitive, and it is in fact true, that you're increasing the number of microstates available to the system. That's why this property is true. Increasing the energy of a system increases its microstates, therefore increases its entropy. And this is one of the implications that temperature is always positive, and this is one of the implications also that you can tell, at least as far as the signs are concerned, which entropies are going up and which are going down by keeping track of what the energy is doing. All right, last piece is pretty straightforward and pretty powerful, in fact. If I've got a system with two parts, A and B here, and I want to know what the entropy for the overall system is, I just have to add up the entropy from the parts. If I've got a system with many parts, I just have to add up the entropies of all the parts, and I've got the total entropy. All right, so that's the extended second law. It's the core of things. There'll be a lot more to say, especially about this first one. Entropy is maximized at equilibrium. That's really the most important one. A lot of implications from that, and we'll come back to it. But before we do that, let's talk about how to actually calculate entropy for practical systems. And we've seen one way already. That's the Boltzmann relationship here, S equals KB log W. We were actually able to calculate an entropy using that rule earlier, but that's just about the only simple case there is. Any real practical case, if you want to calculate the entropy change for DNA, for example, doing something, unwinding or something, then wow, this method would require that you calculate how many microstates that DNA and all of its solvent and everything has, and how that's changing as the change takes place. I mean, there are people who do that kind of thing. In truth, it's the statistical mechanicians who do those kinds of calculations, but they're difficult. A much more practical way to do things in most cases is this rule. This is the traditional way of calculating changes in entropy. It's hard for me to express how great a piece of genius this little simple relationship is. I don't know even, I mean, this was invented in the 1860s, I think, by people who didn't know anything about statistics, who didn't have many of the benefits that we have today. They were just dang smart people, that's the truth. Anyway, I could expound on how this came about and what it means and everything, but just let's not despise this relationship. It's kind of abstract, and we'll do a lot of examples to see how it works, but it's very powerful. All right, I say here that it's usually the practical way to do the calculations, and again, we'll do examples to see what it means, because right now it's not so clear what it means. One thing I will say right now is that what it's saying is that the change in the entropy is equal to the heat change. It doesn't have to do with work, only heat, divided by temperature. And why heat divided by temperature? Well, there's a lot to say about that, but we'll move on. But the other thing to say is that there's this little rev under here. That means reversible. Don't ignore that. The heat change that matters, the heat change that allows you to calculate entropy, is a reversible heat change. And that's true even if the actual process that's taking place is irreversible. If you want to calculate the entropy change for an irreversible process, you have to dream up a reversible change that gets you between the same initial and final state. We'll see examples of that. So this rev is important. It means that you can be fooled, right? If you are faced with a problem, an irreversible process of some kind, you might be tempted to try to calculate the heat change for that irreversible process. That not only will be difficult, it'll give you the wrong answer. You got to calculate the heat change for some process that didn't take place, but was reversible, but connected the same initial and final equilibrium states. All right, we'll see examples. Yeah, here's saying the same thing. Here's state 1, here's state 2. These are equilibrium states. This is the change that's taking place, right, from state 1 to state 2. Here's a nice reversible process. Here's an irreversible process. I say that's the actual one. You got to use the reversible process anyway, despite the fact that that's not what happened, in order to calculate entropy change. Now, if you want to know the heat change for this actual process, well, then you got to do the heat change for the actual process. But if you want to calculate the entropy, you use the irreversible process. You use the reversible process, sorry. All right, examples. We always start with this one, right? Isothermal expansion or compression of an ideal gas. So let's consider an ideal gas in a cylinder. And it's in the presence of a tea bath, and the walls are not insulating, so heat can flow back and forth between the system and surroundings. We say there's 1 mole. We say the temperature in the surroundings is 300 Kelvin. That's room temperature. That's sort of the default standard temperature. 95% of all the problems we do will be at 300 K. We're going to say that the change is easy. It's just start at volume of 1 liter and move to a volume of 3 liters. So 1 liter here, 3 liters there. We're going to do it by 2 different processes. The first one's reversible, see what answers we get that way, and then we're going to do an irreversible process, see what answers we get that way. Someone might be really quick and think, well, Dr. Keller, you just told us that you have to do the calculation as if it were reversible. So maybe, even though it's irreversible, you get the same answer for these 2. Is that true? It's true as far as the system is concerned. It is true. If you're talking only about the entropy change for the system, that's true. But if you talk about the entropy change for the surroundings, it turns out it's not true. The fact that this one's irreversible changes the initial and final state for the surroundings and means that the entropy change for the surroundings won't be the same in this case and in this case, and therefore the overall total entropy of the universe will be different for these two guys. The system entropy will be the same for these two guys, but the surroundings entropy can be different, in general will be different, and therefore the total entropy will be different too. All right, let's look at the reversible case. Let's look at the entropy change for the system first. We have our rule. This is our general rule. The entropy change is, for a small change, is equal to the small reversible heat change for that process divided by T. Since it's an ideal gas expanding isothermally, the total energy change is equal to 0. That means the heat change is equal to the work change. And since we're doing this by a reversible process, these heats and works are the reversible heats and works. And that means that the pressure on the inside and the pressure on the outside are the same. And that means that this work is minus P dV, and we don't have to worry about whether it's external or internal pressure. They're the same. And that means that the heat is plus P dV. The minus sign here cancels that minus sign, which is equal, using the ideal gas law, to nRT dV over V. And if I plug that up in here and take the integral, so I take the integral of both sides, and I plug that in for dq rev, that's what I've done down here. Delta S is the integral from my initial volume to my final volume of the dq rev here. So right, nRT over V dV, that's dq rev, divided by T. And you can see the T's are going to cancel out, and you can see you're going to get dV over V, and so you get this result, nR log V2 over V1. I won't go through the algebra, since I don't know actually if we've done that before. I think we have done that before, and I won't go through the algebra every time. I have this boxed in green, and it says important result there. There's two reasons why this is an important result. It's one of the basic rules that we're going to use. It's going to be possible to combine entropy changes into a whole chain of things and calculate quite complicated things by using rules like this to calculate little pieces along the way. So it's an important result for that. It's one of the panoply of basic results that we'll use throughout the rest of this section. But there's another reason. We got this result earlier, right? We got it from the Boltzmann relationship. Where are we? Way up here. No, not that far. Here. We got it from this earlier when we were talking about the statistics. And here we're getting exactly the same results. Where am I? There we are. But this time we made no reference to statistics. We just used this basic rule and got exactly the same results. So that's at least one indication. It's not an actual proof, but it's consistent at least with the idea that the statistics idea we talked about earlier and this traditional thermodynamic way of doing things really are equivalent to each other. Again, yes, I have this label on here. This is for a reversible isothermal ideal gas. It doesn't work for other cases, but that's an important special case. All right, let's plug some numbers in. We have 1 mole, gas constant's 8.314, that's the R here. Log of V2 is the final V, is 3 liters. V1 is 1 liter, and if you do the arithmetic, that's 9.13. Note the units, they're the same as the gas constant, right? Because this is unitless. 9.13 joules per K. Actually, not per mole, that's a mistake. Joules per K, period. Because we multiplied by moles over here, and that cancels the mole units. So notice the units for entropy. Joules per K, energy per temperature is always the generic units for entropy changes. Joules per K usually. One other issue, as I point out here, is I'm using the gas constant in joule units here, which is an MKS unit. The volume unit that goes with that is meters cubed, But here I used liters instead of meters cubed. Is that all right? Well, it is in this case. It's a little sloppy on my part. I should have converted things to meters cubed first, but it's kind of a pain. It works in this case because, see, the liters cancel out here. The thing that's in the log like this is always a unitless quantity, so it doesn't matter what units you use. If you use liter units, or if you use, I don't know, gallon units or something like that, or ounce units or some crazy English unit, it'll still work. The ratio will be the same. Doesn't depend on the units. And then take the log. All right, so that's one result, this 9.13 joules per K. Is that a big change? Is that a small change? It's a fairly small change. We're going to encounter, most chemical reactions, for example, have much bigger entropy changes than that. All right, so that's the system entropy change. What about the surroundings? Well, now we're going to calculate the entropy change for the surroundings, but it's a reversible process, which means that the changes that take place in the system, the exact opposite changes take place in the surroundings. In particular, whatever work is done by the system, there's no work against friction or any other complications. That's just the negative of the work that's done that goes out to the surroundings. Yeah, no friction here. Combine that with the fact that there's no energy change here. That means that the change in the reversible heat change for the surroundings is equal to the negative of the heat change, the reversible heat change for the system. Notice that I've done this, I hadn't pointed it out before, but whenever there's a surroundings property, I put a little "sir" on there. But I don't put "cis" on the cis. These are system properties, this one and this one. I don't put a little "cis" there, because I just drop it. It just gets up to be a pain to write cis all the time. So whenever you see something that doesn't say cis or sir, that means it's cis. All right, well, in that case, the entropy change for the surroundings, I mean, all the heat changes, all the reversible heat changes are the same. The temperature is fixed, which means that has to be the same too. That means the surroundings entropy change has to be the same, the negative, actually, of the system entropy change. That means when you add these two guys together, you're going to get 0. The total entropy change for this case, for this reversible case, for both system and surroundings is 0. And that's an important result also because this is a general result. It's basically one of the possible definitions of a reversible process. All reversible processes have a total entropy change of 0. Some textbooks and other places define a reversible process to be a process with a total entropy change of 0. So if you ever encounter a process for which the total entropy change is 0, notice not the system or surroundings entropy changes. Those are both not 0. Just the total is. If you ever encounter a process with a total entropy change of 0, that's a reversible process. And vice versa. If it's reversible, then its total entropy change will be 0. Yes, all right, that's what I'm saying here. So, good. All right, now let's look at the irreversible case. A little bit trickier and a little bit more complicated. We're going to start with the same two equilibrium states for the system, state 1 and state 2 here. But since it's irreversible, the process is in between the whole series of changes and stuff that's taking place to go between these two equilibrium states. They may not be equilibrium states at all. They may involve all kinds of violent swirling and explosions and fire and everything else. So I've drawn a kind of a path here in gray, but I drew it in gray and with dash lines because this PV diagram is a two-dimensional plane of equilibrium states, and now we're talking about non-equilibrium states. They're not really even on this diagram. So there's some kind of path between the two, but we can't even draw it properly. This is for the system itself. That's why I put the little internal there. So this is the internal pressure in this case. But over here, we got to look at what's happening in the surroundings as well for this irreversible case. Because remember, for the system, we're going to get the same result. That's what I said earlier. So we're not going to get anything new over here. It's over here where we're going to get some new stuff. And so we got to look at that. I'm saying, and here I'm adding something new to the problem. I didn't say this before. I have to say something new in this case in order to do the calculation for the surroundings in an irreversible case. I have to say what's happening in the surroundings as well. And I'm saying that what's happening in the surroundings is what's showing down here. I'm starting in this irreversible case with a certain pressure inside the system and a certain pressure outside the system. And this surroundings pressure is much lower than the internal system pressure. There's a temperature in here, and that's the same as the temperature in the surroundings because there's a temperature bath. And likewise, it's the same temperature over here. The temperature doesn't change as we do this process. There are little pins that are holding the piston in place because the pressure inside is higher and the piston would move if it could. I take the pins out. What happens? Well, there's a force mismatch, right? A pressure mismatch, which means there's a net force acting on this piston, which means that if the friction is low, this piston's going to shoot, right? And all kinds of swirling and stuff is going to take place. It's possibly a semi-explosive situation, in fact, if the pressure difference is big enough. And so very definitely not equilibrium states, not slow, not gentle. But eventually, there's always a little bit of friction, right? So eventually what's going to happen is the piston's going to shoot up. It'll overshoot, right, because it's got some momentum going. Then the pressure on the inside will get lower than the pressure on the outside, so it'll come back and overshoot again, and it will eventually oscillate down until friction takes away all the extra energy that was generated in the first release, or released in the first release, and eventually it'll settle down and sit at this one place when the pressure on the inside and the pressure on the outside are the same. So that's the thing I'm showing in this diagram in somewhat less graphic form. There's all these non-equilibrium states in between, but I start with the same equilibrium state, with this equilibrium state here with a low pressure on the outside, and I end at the same pressure on the outside. The external pressure hasn't changed throughout the process. The volume has changed, right? The system volume has changed. That means the surroundings volume has changed too. The surroundings volume has gone down. The system volume's gone up. But the pressure hasn't changed. The pressure on the outside stayed the same the whole time. I say that there's a pressure bath on the outside, so this is a situation where the outside here is the rest of Albuquerque, and whatever's going on in this box is not going to change the pressure in the atmosphere of Albuquerque. So the pressure at the end is the same as it was at the beginning. All right. I say here an important point, and I'll summarize some of these important points at the end, but whenever you see this kind of thing, let me erase some of this junk. Too many red marks here. Can't see what I'm writing that's new. Whenever you see this situation, the pressure here and the pressure there are not the same, and the only reason things aren't moving is because of pins. That means if I take these pins out, in the moment, in the nanosecond when I take those pins out, there'll be an unbalanced force, the presence of unbalanced thermodynamics forces, a difference in temperature. T1 is greater than T2, right? So a temperature gap, temperature difference, or a difference in chemical potential also. All these three are thermodynamic driving forces: pressure, temperature, chemical potential, thermodynamic driving forces, all of them. Anytime there's an imbalance in those forces, then you are in a non-equilibrium, irreversible situation. So looking for unbalanced forces is another way to test for whether the process you're carrying out is reversible or irreversible. If it's got unbalanced forces like this one obviously does as soon as the pins come out, then it's irreversible. Yeah, so it's irreversible because the forces are unbalanced, but also because if the forces are unbalanced, then at the moment when this piston starts to move, friction has to start being present, right? However small, there's got to be at least a little friction, or else this thing won't come, it'll just oscillate forever if there's truly no friction. There's got to be at least a little friction or it never comes to equilibrium. And how much friction determines how long it takes to get to equilibrium. If there's very little friction, it might take, a day to come to equilibrium. If there's a lot of friction, it might never oscillate at all. It might just come right to equilibrium in, 1/2 second or something. But there's got to be a little bit of friction, and so there will be friction present, and that's another test for whether it's an irreversible process or not. If you recall from up above, a reversible process has no friction. An irreversible process does have friction. All right. So now let's look at the entropy changes for this irreversible process. And let's look first at the system entropy changes. But I already said what's going on in this case. We still have to use this rule, which requires that we use a reversible heat change. It's the same initial and the same final states as in the reversible case above, so we've got to use the reversible path even though this is not a reversible process. And that means the calculation is going to be exactly the same. We're going to use the reversible path again, and that means that the entropy change for the system is going to be the same as it was before. Yeah, and I say that just a little bit, well, in a different way, and maybe that's useful. You should pretend, in this case, that the external pressure in this reversible process, P2 out here, or P external out here, is always matched with the internal pressure, the system pressure. So that as the piston expands and the internal pressure goes down, the external pressure is also being decreased, by some experimenter outside, say, so as to always keep these pressures matched to each other. That's what it means to carry out a reversible process. There's never a force, there's never a pressure imbalance. All right, so our delta S is nR log V2 over V1, same as before. Remember that the work for this case is minus nRT log V2 over V1, so there's a T here that isn't present in this case, because that's equal to minus Q, right? And therefore Q is equal to nRT log V2 over V1, and therefore delta S, which is Q over T in this case because the temperature is constant, Q rev, is equal to, well, you just take this and divide it by T, and that's what we got, right? nR log V2 over V1. So you can remember this result and remember why you get that result, because of all these other results. Remembering all the results as a cluster is sometimes a useful way both to understand and to remember at the same time. All right, now the surroundings. This is the tricky part. The initial and final states are not the same as they are for the system. For the surroundings, we're starting with a state like this, where there's a pressure of P2 on the outside. But in order for this to be, we need a reversible process, right? We need a dq rev. If we're going to calculate delta S for the surroundings, we need a dq rev. We need a reversible process. That means these pressures have to be balanced with each other. That means I got to start the system in a different state than it actually had in real life. I got to start it with a pressure P2, a low pressure, same as the outside, to start with. My initial state doesn't have the same pressure as it did in the first calculation. And now I just allow the barrier to move a little bit, the piston to move a little bit, and the pressure stays the same all the way across because there's a P bath out here and that external pressure never changes, but the volume changes, right? So in this case, the Q change, the heat change for the surroundings for a reversible process, delta U is 0, right? Still, because there's no energy change for the system, and therefore there's no energy change for the surroundings either, right? Any energy that the surroundings gained or lost had to come or go to the system. So if the system can't change its energy, neither can the surroundings. So that means that Q is equal to minus W for the surroundings as well. But the work for the surroundings is the negative of the work for the system, so Q for the surroundings is the same thing as the work for the system. And we know the formula for that. It's minus P delta V. P is our pressure, which is the same in both cases now, right? So either internal or external times whatever the volume change is. And so dq for the surroundings is dq rev for the surroundings. Let me make that change actually, because I should have put, Yeah, that's right. dq rev for the surroundings. And therefore, delta Q for the surroundings is Q rev for the surroundings divided by T. That's minus P2 delta V over T. And now using the ideal gas law, it gets a little bit more complicated. There's my final algebraic expression. Now I plug the numbers in. V2 is 3, V1 is 1, V2 is 3, N is 1, and so on. And that gives me a minus 5.54 joules per K. And again, that's not per mole. That's just joules per K. Okay. It's a minus sign because, yeah, I didn't point that out before, but let me point out now that up here, when we calculated the entropy change for the system, it was a positive value. That's because the system expanded, right? It makes sense. The system expands, molecules have more freedom, entropy, number of microstates increases, entropy increases. Down here, when we're expanding the system, we're compressing, in a sense, the surroundings. The surroundings is practically infinite, but still, the surroundings is losing volume. So we expect a negative entropy change for the surroundings, and in fact, that's what we get. But notice it's not as big. It was positive 9.13 for the system. It's only minus 5.54 for the surroundings in this irreversible case. And that means that the total entropy is no longer zero. It's an irreversible process, right? So 9.13 for system, minus 5.54 for surroundings, leads to a net plus 3.59 overall, which means that this is a spontaneous process, right? Which we knew already, right? If the pressure was higher, I mean, going back to the original case here, the pressure was higher on the inside than on the outside, and we let these pins out, we know it's going to go. And if it goes, if it's spontaneous, then there must be a positive entropy change. Overall, the entropy of the universe must go up. And that's what the calculation says. Because the entropy change overall is not zero, this is an irreversible process. Every spontaneous process is irreversible. Okay, just to summarize a little bit, let me say something about this. We've talked about various properties of reversible processes, and before this, let me put them all in one place. If the entropy change, the total entropy change for system and surroundings is zero, then it's reversible. If the forces are balanced at all points, then it's reversible. If we're always at equilibrium, then it's reversible. And if there's no friction, then it's reversible. If any one of these properties isn't true, then it's irreversible. And the reason for that is that all these things imply each other. So if there's no entropy change overall, then the forces must have been balanced. That means you must always have been in equilibrium. That means there must not have been any friction. So all of these things imply each other, and that means they all have to be true at once in order for it to be a reversible process. All right, there's one more example here that I'm going to do next, but let me stop there.